standard method of calculating circuit ampacity uses the conductor size and type, ambient temperature, and insulation type. This approach assumes the circuit operates at its maximum continuous load. The optional method, however, allows for ampacity reduction based on load diversity and short circuit protection. Load diversity acknowledges that not all loads operate at peak demand simultaneously. Short circuit protection ensures the circuit has adequate protection, limiting fault current to a safe level. The optional method often results in smaller service sizes because it considers factors reducing the actual load. Load diversity plays a significant role. By factoring in the probability that all loads won't peak simultaneously, a smaller circuit size is permissible. Short circuit protection further reduces risk. With adequate protection, the risk of overcurrent damage decreases, enabling a smaller service. However, the optional method isn't always the best choice. Firstly, the standard method provides a more conservative ampacity estimate, ensuring the circuit handles its full load in worst-case scenarios. Secondly, the optional method relies on assumptions about load diversity and short circuit protection. If these assumptions are inaccurate, the circuit may struggle to handle the actual load. Thirdly, unknown or variable loads make the standard method more reliable. If the loads are unpredictable, a conservative approach is safer. Ultimately, the decision depends on the specific application and available information. For critical circuits or when load and short circuit conditions are uncertain, the standard method is preferred. The optional method can reduce service size for non-critical circuits with well-defined load diversity and short circuit protection. It is important to consult local electrical codes and regulations to ensure compliance with all applicable requirements. Electrical codes like the National Electrical Code, or NEC, are designed to ensure safe installation and operation of electrical systems. NEC Section 220.42 covers general lighting loads. For dwelling units, a unit load of 3 volt amps per square foot is used. For other occupancies, the unit load varies depending on the type of occupancy. NEC Section 220.44 addresses small appliance and laundry loads in dwelling units. 2 or more 20 amp small appliance branch circuits are required for the kitchen, pantry, breakfast room, dining room, and similar areas. These circuits are calculated at 1500 volt amps each. A minimum of 120 amp laundry branch circuit is also required, also calculated at 1500 volt amps. NEC Section 220.50 covers fixed appliance loads. For appliances fastened in place, the nameplate rating of the appliance is used. If both the volt ampere and wattage ratings are given, the volt ampere rating is used. NEC Section 220.51 addresses motor loads. For continuous duty motors, the full load current rating is used. The largest motor in a group is calculated at 125% of its full load current rating, while the other motors are calculated at 100%. NEC Section 220.52 covers electric heating loads. For electric heating, the nameplate rating of the heating equipment is used. If the heating is intermittent, a demand factor may be applied. NEC Section 220.53 addresses air conditioning loads. For air conditioning equipment, the nameplate rating of the equipment is used. If the air conditioning is intermittent, a demand factor may be applied. NEC Section 220.54 covers electric vehicle supply equipment, or EVS loads. EVS loads are calculated at 100% of the maximum current rating of the charging equipment. NEC Section 220.60 addresses non-coincident loads. Where it is unlikely that 2 or more loads will operate simultaneously, a demand factor may be applied. Common examples include heating and air conditioning, or cooking equipment and electric water heaters. NEC Section 220.61 covers optional calculations for dwelling units. The optional calculation method allows for a reduction in the service size based on certain assumptions. For dwelling units with electric heat, air conditioning, and cooking, the first 10 kilowatts of load are calculated at 100%, and the remaining load is calculated at 40%. NEC Section 220.80 provides an optional calculation for new restaurants. This method allows for a reduction in the service size based on certain assumptions about the restaurant's load profile. NEC Section 220.82 offers an optional calculation for existing dwelling units. This method allows for a reduction in the service size based on the existing load profile of the dwelling unit. Factors such as historical energy consumption and the types of appliances in use are considered. It's crucial to understand that the standard method and optional methods are not mutually exclusive. In some cases, a combination of both methods can be used to determine the appropriate service size. For example, the standard method might be used to calculate the general lighting and receptacle loads, while the optional method might be used to calculate the heating and air conditioning loads. When applying demand factors, it is important to have a clear understanding of the load characteristics and operating schedules of the various electrical loads. Demand factors are based on statistical data and engineering judgment, and they may not be applicable in all situations. For example, a demand factor for general lighting might be appropriate in an office building where the lighting is typically used during daytime hours, but it might not be appropriate in a retail store where the lighting is used extensively during evening hours. The standard method for calculating electrical loads is outlined in Article 220 of the National Electrical Code (NEC). This method provides a systematic approach to determining the minimum ampacity required for various circuits in the overall service. Here's a breakdown of the key steps and considerations within the standard method. Firstly, general lighting loads. Calculate the general lighting load based on the square footage of the building or occupancy. The NEC provides specific volt-ampere per square foot values for different types of occupancies. Secondly, receptacle loads. Determine the receptacle loads based on the number of receptacles and their intended use. The NEC provides specific volt-ampere values for different types of receptacles. Thirdly, appliance loads. Calculate the appliance loads based on the nameplate ratings of the appliances. For permanently connected appliances, the nameplate rating is used. For cord and plug connected appliances, the NEC provides specific volt-ampere values. Fourthly, motor loads. Determine the motor loads based on the horsepower and voltage ratings of the motors. The NEC provides tables that list the full load current for motors of different sizes and voltages. Fifthly, heating and air conditioning loads. Calculate the heating and air conditioning loads based on the nameplate ratings of the equipment. For resistance heating, the nameplate rating is used. For heat pumps and air conditioners, the NEC provides specific volt-ampere values. Sixthly, other loads. Account for any other loads that may be present, such as electric vehicle charging equipment, welders, or X-ray equipment. The NEC provides specific requirements for these types of loads. Seventhly, demand factors. Apply demand factors to the calculated loads to account for the fact that not all loads will be operating at the same time. Demand factors are based on statistical data and engineering judgment. Eighthly, service size. Determine the overall service size based on the sum of the calculated loads, taking into account any applicable demand factors. The service size must be large enough to supply all of the loads without overloading the system. The optional calculation methods, as described in Article 220 of the NEC, offer alternative approaches to calculating the electrical loads for a building or occupancy. These methods are often used to reduce the service size and associated costs, particularly in dwelling units. Here's a detailed explanation of the key aspects of the optional calculation methods. Firstly, dwelling unit optional calculation. This method is primarily used for dwelling units and takes into account the diversity of loads within a typical household. It allows for a reduction in the overall calculated load based on the assumption that not all appliances and equipment will be operating simultaneously. The dwelling unit optional calculation involves several steps. 1. Calculate the general lighting and receptacle load at 3 volt-amps per square foot. 2. Calculate the small appliance and laundry loads at 1500 volt-amps for each small appliance circuit and laundry circuit. 3. Calculate the range load based on Table 220.55 of the NEC. 4. Calculate the air conditioning and space heating loads based on the nameplate ratings of the equipment. 5. Apply a demand factor of 40% to the portion of the total load that exceeds 10 kilowatts. Secondly, optional calculation for schools. This method is used for schools and takes into account the diversity of loads within a typical school building. It allows for a reduction in the overall calculated load based on the assumption that not all classrooms and facilities will be in use simultaneously. Thirdly, optional calculation for restaurants. This method is used for restaurants and takes into account the diversity of loads within a typical restaurant kitchen. It allows for a reduction in the overall calculated load based on the assumption that not all cooking equipment will be operating simultaneously. Fourthly, optional calculation for multifamily dwellings. This method is used for multifamily dwellings and takes into account the diversity of loads within a typical apartment building. It allows for a reduction in the overall calculated load based on the assumption that not all apartments will be using their appliances and equipment simultaneously. Fifthly, considerations for using optional methods. The optional calculation methods are not always applicable. They are only permitted when the building or occupancy meets certain criteria, such as having a diverse mix of loads and a well-defined load profile. The authority having jurisdiction, OJ, has the final say in whether or not the optional calculation methods can be used. The use of demand factors is a critical aspect of electrical load calculations. Demand factors are multipliers applied to connected loads to estimate the maximum load that is likely to be drawn at any given time. They account for the fact that not all connected loads will be operating simultaneously or at their full rated capacity. Here's an overview of demand factors and their application. 1. Definition of demand factor. The demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system or the part of the system under consideration. It is always less than or equal to 1.0. 2. Purpose of demand factors. Demand factors are used to reduce the calculated load, which can result in a smaller service size and lower equipment costs. They allow for a more realistic assessment of the actual load that the electrical system will need to handle. 3. Application of demand factors. Demand factors are applied to various types of loads, such as lighting, receptacles, appliances, motors, and heating and air conditioning equipment. The specific demand factors used depend on the type of occupancy, the nature of the loads, and the historical load patterns. 4. Demand factors in the NEC. The NEC provides demand factors for various types of loads in Article 220. These demand factors are based on statistical data and engineering judgment. 5. Factors affecting demand factors. The demand factor for a particular load depends on several factors, including the type of occupancy, the number of connected loads, the diversity of the loads, and the operating schedule of the loads. 6. Considerations for using demand factors. When applying demand factors, it is important to have a clear understanding of the load characteristics and operating schedules of the various electrical loads. Demand factors are based on statistical data and engineering judgment, and they may not be applicable in all situations. 7 examples of demand factors. Firstly, lighting. In an office building, the demand factor for general lighting might be 0.8, indicating that only 80% of the connected lighting load is likely to be in use at any given time. Secondly, receptacles. In a dwelling unit, the demand factor for general-purpose receptacles might be 0.5, indicating that only 50% of the connected receptacle load is likely to be in use at any given time. Thirdly, motors. In an industrial facility, the demand factor for motors might vary depending on the type of motors and their operating schedules. Motors that operate continuously might have a demand factor of 1.0, while motors that operate intermittently might have a lower demand factor. Short-circuit protection is a critical aspect of electrical system design and is essential for ensuring the safety of personnel and equipment. Short-circuit protection devices are designed to quickly interrupt the flow of current in the event of a short circuit, which is an abnormal condition characterized by low resistance paths between 2 points in an electrical circuit. Here is an overview of short-circuit protection. Firstly, causes of short circuits. Short circuits can be caused by a variety of factors, including insulation failure, accidental contact between conductors, and equipment malfunction. Secondly, effects of short circuits. Short circuits can cause a rapid increase in current flow, which can lead to overheating, arcing, and equipment damage. In severe cases, short circuits can also cause fires and explosions. Thirdly, types of short circuit protection devices. There are several types of short circuit protection devices, including fuses, circuit breakers, and ground fault circuit interrupters, GFCIs. Fourthly, fuses. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when the current exceeds a predetermined value. Fuses are simple, reliable, and inexpensive, but they must be replaced after they have been used to interrupt a short circuit. Fifthly, circuit breakers. Circuit breakers are overcurrent protection devices that use a mechanical mechanism to open the circuit when the current exceeds a predetermined value. Circuit breakers can be reset after they have been used to interrupt a short circuit, making them more convenient than fuses. Sixthly, ground fault circuit interrupters. GFCIs are designed to protect against ground faults, which are a type of short circuit in which current flows through an unintended path to ground. GFCIs detect even small amounts of current leakage to ground and quickly interrupt the circuit, preventing electric shock. Seventhly, coordination of short circuit protection devices. It is important to coordinate short circuit protection devices to ensure that the device closest to the fault interrupts the circuit first. This minimizes the amount of damage that can occur and helps to prevent cascading failures. Eighthly, short circuit current rating. Short circuit protection devices have a short circuit current rating, which is the maximum amount of current that the device can safely interrupt. It is important to select devices with a short circuit current rating that is adequate for the available fault current at the point of installation. Ninthly, standards and codes. Short circuit protection is governed by various standards and codes, including the NEC. These standards and codes provide detailed requirements for the selection, installation, and coordination of short circuit protection devices. When evaluating load diversity in electrical load calculations, several key factors should be taken into consideration to ensure accurate and reliable results. Firstly, occupancy type. The type of occupancy plays a significant role in determining load diversity. Different occupancies have different load profiles and usage patterns. For example, a residential building will have a different load profile than an office building or a retail store. Secondly, load types. The types of loads present in the electrical system also affect load diversity. Different types of loads have different operating characteristics and usage patterns. For example, lighting loads may have a different diversity factor than motor loads or heating and cooling loads. Thirdly, operating schedules. The operating schedules of the various loads in the electrical system are critical for determining load diversity. If multiple loads operate simultaneously or have overlapping operating schedules, the load diversity will be lower. If the loads operate at different times or have non-overlapping schedules, the load diversity will be higher. Fourthly, historical data. Historical data on the actual loads in the electrical system can be valuable for evaluating load diversity. By analyzing historical data, it is possible to identify patterns and trends in the load profiles and usage patterns. Fifthly, engineering judgment. Engineering judgment is often required to evaluate load diversity, particularly when historical data is not available or when the electrical system is serving a new or unique type of load. Engineers use their experience and knowledge to estimate the load diversity based on the expected usage patterns and operating characteristics of the loads. Sixthly, NEC requirements. The NEC provides guidance on load diversity in Article 220. The NEC specifies demand factors for various types of loads and occupancies, which can be used to account for load diversity in electrical load calculations. Seventhly, coordination with utility. It is important to coordinate with the local utility company to ensure that the electrical system is designed to meet the utility's requirements. The utility company may have specific requirements for load diversity and demand factors. To recap, the standard method calculates circuit ampacity based on conductor size, type, temperature, and insulation, assuming maximum continuous load. The optional method allows ampacity reduction based on load diversity and short-circuit protection. Load diversity accounts for non-simultaneous peak demands. The optional method yields smaller service sizes because it considers these factors. However, the standard method offers a more conservative estimate, suitable for critical circuits or unknown loads. The optional method is applicable when load diversity and short-circuit protection are well defined in non-critical circuits. Consider local codes, regulations, and NEC guidelines for safe electrical system installation and operation. Demand factors, as provided in the NEC, are crucial for accurate calculations, allowing for realistic load assessments. Short-circuit protection is essential for safety, using devices like fuses and circuit breakers to quickly interrupt abnormal current flow. Coordinating these devices ensures the closest to the fault trips first, minimizing damage. Evaluate load diversity by considering occupancy type, load types, operating schedules, historical data, and engineering judgment. Always coordinate with the utility company to meet their requirements.